Hello, and welcome to the webcast titled Leveraging VPX for Processing Intensive Application. My name is John McHale, Group Editorial Director with Military Embedded Systems, the SOSA Special Edition, and the FACE Special Edition. I'm also moderator for today's event. To learn more about Military Embedded Systems, please visit militaryembedded.com. You can check out our articles, blogs, podcasts, and more on military technology. Now let's get to the webcast. Our speakers today are Ryan Jansen, Chief Architect at New Wave DV, and Nigel Forrester, Director of Strategy with Concurrent Technologies. The event is sponsored by New Wave DV and Concurrent Technologies and hosted by Military Embedded Systems Online and Open Systems Media. Now, before we get started, I've got some housekeeping items I want to go over with you. This and all Open Systems Media webcasts are copyrighted. It may not be recorded or used in any way without the express written consent of Open Systems Media. The webcast will consume about 40 to 45 minutes, leaving the remaining time for the live question and answer session. Some of you might notice that our console has a new look and feel for 2023, so let me take you on a tour. You'll find on the right-hand side an area where you can enter your questions in real time. And we encourage you to ask those questions throughout the session while the question is still fresh in your mind, and we'll address as many as we can during the closing Q&A portion. If you have a question for a specific speaker, please note so at the beginning of your question, or I'll offer it to both of them. If you have a question pertaining to the event operation itself, one of our technicians will get back to you during the webcast. Please note that as much as we'd like to, we may not get to all your questions today. In that case, someone may get back to you after the event with more information. Across the way on the left-hand side, there's a resources section. That's where you can find the slides being presented today. Below that, you can also view today's speaker information. Now, there's two more features I want you to take a look at that we're excited about. Your console is now customizable insofar as you're able to manipulate all these widgets, Q&A, resources, and presenters for your ideal viewing experience. Expand them to get a closer look, or close them to have the presentation window automatically resize around them. For maximum screen size, close them all, and or utilize the full screen control in the upper right-hand corner of the presentation window. To bring them back, simply click on the buttons in the bottom middle dock. In an effort to make the webcast even more accessible, we've also added closed captioning capabilities in nearly a dozen languages, including English. To enable this functionality, click on CC in the upper right-hand corner of the presentation window and select your language of choice from the drop-down menu. This webcast will be archived online at the same URL you used to join today's live session and be available within 48 hours. Once up, it'll be available for at least 1 year. So now I'd love to turn it over to our first speaker, Nigel Forrester. Nigel, please take it away.
So before I conducted my slides, I tried to sort of position myself into thinking, well, what do we mean by leveraging VPX for processor-intensive applications? And also bearing in mind that there's quite a large number of people who've registered, some of whom are probably VPX experts and some of whom are VPX novices. So I'll try and capture something that works for all of you. I'll try to avoid most of the jargon and lexicon, but please do feel free to answer questions, as John said, and we'll try and get to those at the end. If we can't, we will cover them later on. So just very briefly, what the Concurrent technologies do, well, we fundamentally make mainly the plug-in cards historically. We've been doing VPX plug-in cards for more than 15 years. And we've also now moved into integrating those into both development and rugged systems. So from a perspective of, where are our unique propositions, we are a UK-based company. We design and we manufacture the products in our UK factory. We also now manufacture these products in the US through a contract manufacturer, which means we're able to help some of our US systems integrators even more. So I like this diagram here particularly because it sort of encaptures what most of the typical VPX users are trying to do. So most of the presentation is going to be focused on defense type applications, but that's not VPX not wholly used for defense. But the original VPX specification, which was standardized by the VITA organization, was VITA 46, was further enhanced by an update called VITA 65, colloquially known as OpenVPX. And really the problem with OpenVPX, or challenges with OpenVPX, was that it was so open that it left a lot of capability to the manufacturer. So we could choose to populate different pinouts on user I/O pins. And so that didn't really meet many of our key customers' use cases. And so this CMOS architecture was one of the first, and then subsequently has been the SOSA open group, who have fed back in some key updates to the VPX specification to enable some really critical features. So the most important thing is that VPX, if you're using the latest version or the latest profiles, enables very easy technology upgrades or insertions, which means that you can boost your system capability or use best-in-class payloads from any of the vendors out there. It also enables you to easily reconfigure the platform. So you might start with something that is fixed for a particular type of application. You might want to either extend that to a new version of the same application, or maybe add in a new application into that by workload consolidation. And that's been cleverly thought out within the remits of the specification. It's very much designed to augment functionality as you go, and hopefully you'll get a good flavor of that as we go throughout the webinar. So let's start at some of what I called the sort of the building blocks, if you like, the sort of the basics. So what I'd firmly recommend is that if you want to leverage the real benefits of VPX for processor intensive applications, that you make use of the open off the shelf, if you like, building blocks that are available, which come in a whole host of different capabilities, from backplanes, chassis, plug-in boards, mezzanines to add additional functionality. So there's a huge amount around. There's a massive ecosystem now. And so it enables you, whether you're building perhaps a radar application or a 360-degree situational awareness computer, or maybe even an AI actionable intelligence system, there are likely to be building blocks out there that you can use, but it is a completely open standard. So it means that you still have the ability to design your own, or have a custom payload designed or custom chassis designed to your needs. So some of those basic building blocks I've got here, basic, that's probably the wrong term. Fundamental perhaps would have been a better term, because there's actually a lot of technology in some of these. Even something as simple as a backplane, there is actually quite a considerable amount of technology there to enable the high bandwidth capabilities that we have within VPX. The backplane's typically now between 1 to 12 slot, and there are cutouts, as you can see in the picture here, for RF and optical connections. And we'll talk a bit more about that, because that's another key benefit of VPX. And these backplanes typically fit into either development chassis, so this is an open frame chassis, enables easy access for debugging and development, and then into deployment, where you have a more rugged chassis that is qualified to whatever level you need it to be qualified to. So there are now a whole range of these backplanes available with different pinouts. We're going to look at one of those in a minute. But the really neat feature of VPX is that from a get-go situation where you might not know exactly what connectivity you need on the backplane, you can actually build your own. So within this type of development chassis, they very often come with what are called power and ground backplanes. So that means they only have the 12 volts and power and ground hardwired into the backplane, and you as a user make the other connections via what are called Meritech cables. So it's a flexible way that you can actually interconnect at the back of the backplane, which it enables you to sort of get going really quickly if you don't have a backplane to your specific needs. So I'm going to look at one specific example, and both this diagram here and the picture are courtesy of one of our partners, Elmer Electronic. They've got some really nice diagrams. They're better than the ones that I drew up myself, so I'm sure they won't mind me sharing these with you. But this is it's a typical backplane, and this is a 6-slot backplane. So you can see there are 6 vertical rows, and the interconnections that are made on the backplane are shown with the lines here. And the backplane is split into a number of different regions. So let's start in the middle with the green control plane signals. So those are designed to enable things like control configuration type messages, very low latency, perhaps small packets of information between the various payload cards. And then the yellow section above is the data plane. And this is designed for much higher bandwidth, interconnection between payload cards, typically, where you're sharing high volumes of data at high bandwidth rates. And within VPX systems today, most of the control and data plane signals are now Ethernet. So historically, the data plane was perhaps more typically PCI Express, but with the latest version of the spec, that has migrated to Ethernet. However, the blue expansion plane connections, where you can see there are a couple of point-to-point connections between slots 1 and 2, and slots 5 and 6 in this particular system, these are typically PCI Express for high bandwidth local interconnects between adjacent pairs of cards. And then you've also got, in red, clock signals. So these are timing signals that go between the cards so that you can synchronize the payloads. And you have at the bottom here the IPMC, which is a management interface, which again is completely standardized within VPX. And then shown diagrammatically at the top, although actually, if you look at the backplane picture on the right, it's actually towards the bottom of the backplane. You can see that there are some apertures on some of these slots in this particular backplane example, where you can fit RF or optical connections. So what we're going to do is going to look at that in a little bit more detail. And take it a step at a time. So if you're building anything that's bigger than about a 3 or 4 slot system, you're probably going to need a switch to interconnect all of those payload cards. So I've got the slot 4 is a switch slot on this backplane, which is highlighted. And you can see that there are data and control plane connections and clock connections from the switch card out to the other cards. So typical example of a switch might look something like this. It's a bit of an eye chart with the block diagram on the left. I'm not going to go through that in any significant detail, but what I am going to point out is that if you look at the control plane, this is typically now 10 gigabit Ethernet, so 10G base KR, and the data plane on this particular switch is 100 gigabit Ethernet. With 40 gig or 10 gig optional, but it will run it up to 100 gigabit Ethernet. And this particular switch is what's called a dual enclave switch. So there are 2 physical Ethernet switch components on the board. They're not as standard interconnected, so they are completely separate so that you can have proper red-black separation for security reasons. However, there is the option to put a bridging module between those two, or it could be an encryption module between those 2 switches for customization purposes. And the other thing to note is that these switches typically are layer 3 with some layer 4 routing protocol capability. And that's so that you can actually interconnect other adjacent equipment or even WAN-based equipment. And that's typically done by these front panel uplink, downlink ports on the system. So having selected a switch, the next thing you need to do is to look at whether you need a timing card in your system. So not all applications need synchronized timing. So if you're building a 360-degree situation awareness, you probably don't need to synchronize your cameras incredibly accurately. But if you're building a signal processing system with lots of FPGA devices that have to be tightly coupled, you almost certainly do need a timing device to synchronize those. So what the timing card does is predominantly it provides radial clock outputs to all of the other payload cards and even the switch card in that system. And if we look at a typical example of a timing plug-in card, it might look something like this. So the key here is that you have both in VPX land a ref clock output to each card in the system, and that ref clock is typically programmable between 10 and 100 megahertz. And you also have an aux clock, radial clock signal to each payload card, and the aux clock is a 1 pulse per second type card. There's a lot of other functionality on this block diagram, which is going to go through some of that in a minute. And that's because typically these the timing payload card also provides assured position and navigation capability to VPX systems. I just want to, in fact, just go back to this slide here. You can see if you look at the actual picture of the card, at the top right-hand corner, you can just make out this sort of metal former with some holes in. This is an example of how this is implemented in VPX, so that there is a potential to have an aperture in the backplane where you can fit either optical or RF capability that directly connects from a connection on the front of the chassis via a cable to one side of this former, and then the board connection is either via cable or actually it can be via a direct PCB mount. So this is really quite a unique feature of VPX, and there are a number of different variations of the standard. This one is 67.3, but there's also a 66, VITA 66 standard for optical modules, and there are different numbers of hole positions, if you like, and there can be a mixture of RF and optical connections. There's all manner of different capabilities that you can build into your system there, which is a very unique capability of VPX. So I talked a little bit about the assured position and navigation side, and that is very much angled because each of these timing cards typically has an RF feed which comes from a GNSS or GPS antenna. And that GNSS signal typically disciplines a quantum chip scale atomic clock. And that supplies then these radial clock signals, which are shown in blue and red, to each of the payload signals via some sort of clock synchronization type circuitry. I'll move on to the next slide. The key here is that, and we've seen this a lot in practice, if anybody's been following the news over the last year in Ukraine, that the GNSS satellite constellation is very easy to jam or deny. And so there has to be a way of enabling the timing to keep going in the event of that happening. And that's exactly why the chip scale atomic clock is disciplined until the GNSS signal is denied. And at that point, it is then, the chip scale atomic clock is free running. So obviously you get a slight reduction in stability. So with the GNSS signal, you're probably talking about a stability somewhere around 10 to the minus 14. Without the GNSS signal, then you're relying on the chip scale atomic clock, and your stability falls a little bit, about 10 to the minus 10. There's a lot of work underway throughout the globe to actually enhance the quantum capabilities of these chip scale atomic clocks. And so I think over the next few years, we're going to see some fairly significant advances there, but they're pretty amazing devices to keep that amount of timing stability without an external synchronization for as long as they do throughout an interesting temperature range. And the other thing I want to just briefly mention about these timing cards is that they are very suitable and often used to provide grandmaster timing sources for either other adjacent systems in the same platform or completely remote platforms. So it does that via IEEE 1588 precision timing protocol, which flows across those Ethernet interfaces that we talked about. So the actual timing clock, whilst it doesn't have a data plane connection, it does have your 10 gig control plane connection, which is used for the precision timing protocol and a lot of other capability to set the card up and configure it and run it during its operational mode. So after the timing card, the next thing I want to talk about is the payload card. And this is probably the biggest part of the VPX system. And this would fit in this particular backplane. There are 3 payload slots. There's slot 2, 5, and 6. I've just highlighted one slot here, slot 5. And these payloads come in all different flavors. So it might be an FPGA, and Ryan's going to tell you a little bit about some of the new wave FPGA accelerators. It might be a CPU. It might be a GPGPU. And historically, some of these have been sort of very much standalone. So the CPU is very much a standalone card. Historically, as I said, quite often the FPGAs and GPGPUs were paired with a CPU. That's not always the case these days. They are capable of running completely standalone. but it's going to be, the whole idea of the specification is that you can mix and match your payload cards to whatever functionality you need without a significant change in the platform. So if I concentrate on the compute intensive payload slots, the really interesting thing is that there is basically one profile with two options. So the little diagrams here, these come directly from the VPX specification, and they're trying to diagrammatically show you what happens. So if you look at the very top of these diagrams, the bit in red that's marked P0, that is the effectively the power management type of the signals for VPX come over on there. The next bit down, which goes right down to the bottom of the blue bit on the left diagram, is the P1 connector in VPX 3U, and these are 3U VPX, I should say. For 6U VPX, you have more connectors, so it's a little bit, you've got more options there. In 3U, the P1 connector has effectively your control, data plane and part of the expansion plane, and then the whole of the rest of the P2 connector in the diagram on the left is blank, whereas on the diagram at the right, you've only got half of that aperture blank, but that then gives you the option to have a wider expansion plane. So in this case, you'd have a by 16 expansion plane, whereas on the diagram on the left, you have a by 8. So if you have only one GPU or FPGA card to pair up to in an adjacent slot, perhaps the diagram on the left is maybe the better option. If you have two cards and you want to have a by 8 PCI Express link going to both of them, then maybe the diagram on the right is the better choice. So if we quickly go through that, the implementation is that by ultra thin pipe, what they mean there is that that's capable of running something like a 10G base KR interface. So it's basically a one pair of bidirectional signals. So on the control plane, that's typically 10 gig now. On the data plane, in modern VPX systems, you have actually two data plane connections theoretically. The bigger of the pipe now is what's called a fat pipe. So that's 4 pairs of differential signals. And that's capable and is not only capable, but is supporting up to 100G base KR4 implementations today. And then there's a second data plane, which is 10G base KR capable. And then we talked about the expansion plane, which is either by 8 or by 16 for these two profiles. So if you look at the compute intensive type of card, the sort of typical example here is designed to pack as much processing capability as possible. And I'm using a CPU as an example here. I'm sure Ryan will tell you about some of the FPGA devices that they have. So in this case, this particular card has a 10-core Xeon processor chip. It has up to 128 gigabytes of DRAM, 2 terabytes of direct attached storage with security capabilities, as well as the 100 gig Ethernet and the PCI Express implementation. So as I said, trying to pack as much compute capability, but without any flexibility for I/O. It's all about how much processing can you get in a physical form factor. So if you want I/O capability, then you have to use this I/O slot, which on our example backplane was in slot 1. And in this case, I've got another nice example product here, where you can see the difference is that on the backplane, which is some of the bottom signals on this diagram here, or if you look at the top right for the little diagram that comes from the VPX specification, you can see that there is allocated specific signals for video, USB, storage, and also most importantly for XMC I/O. So the whole point of this type of configuration is that you can be as flexible as possible. Good example being we've very recently had an application where we needed to support both RS-42 and MILCAN, and we did that via a plug-in mezzanine that sat on top of an I/O intensive processor board. It's a very neat and simple way of doing it and very cost effective. So that's all I've got prepared on the actual sort of payload side, but I did want to talk one more very fundamental thing, and that's about cooling capability or cooling strategy, because historically, most VPX deployments that we've seen have been using conduction cooled cards. And so if you look at the diagram on the top, the green bit along the bottom of figure 1 is the PCB, and then you've got your hot, let's say it's an Intel processor. You've got a thermal junction between the thermal interface material and the heat frame that goes on top of it. And then in these conduction cooled cards, they have wedge locks, which have a thermal junction to the heat frame, and then you have another thermal junction to the chassis, and then you finally have a fourth thermal junction to the actual cooling capability of that chassis, being it air, conduction cooling, or so on. So fundamentally, you have 4 thermal losses in a traditional VPX cooling methodology. So over the last 18 months, we've started to see quite a number of applications where they need significantly more performance, but in a swap-C optimized variant. And so we've started to see quite a number of customers deploy what's called airflow through. And the benefit of airflow through is that you directly get air much closer or through, if you like, between the sort of the heat frame itself. And that means from a thermal loss point of view, you get about half a thermal loss. If you look at it in very simplistic terms, it gives you the capability to have much better performance there. If I look at that in a different way, there's a diagram here which shows how the air flows between both the base card and a mezzanine card. So they both cooled very effectively, and that does enable significant more performance. So wrapping up, in summary, if you want to leverage VPX for processor applications, you have a number of key benefits. You can get some incredible performance out of these very small cards, up to 100 gigabit Ethernet as between each slot. You can select the best in class now, so there's no vendor lock-in, which is a significant improvement from a few years ago. You can upgrade when required as well. So that's really key from a total cost of ownership perspective, because it doesn't tie you into a single solution that's then not upgradable. And it very much does bring that cost of ownership, if you're using a COTS product, significantly reduces that, and it also significantly reduces your time to market. So with that, hopefully that's been an interesting introduction. I'm going to hand you over to Ryan. Thank you very much.
Thanks, Nigel. It was a great, nice overview of VPX and really showing how you can use VPX to leverage processing intensive applications. So, Nigel did a great job of explaining all the different types of modules, how the standard works. I want to continue the discussion and really focus on how VPX can enable us to use all the latest and greatest technology that is out there, especially on the commercial side and the high performance computing world. New Wave DV, we're a company that specializes in FPGA-based VPX and XMC modules. Most of our modules are focused on high-speed serial interface I/O, both electrical and optical, and feature a large FPGA with PCI Express interface to some of the other types of modules that Nigel mentioned, whether they were CPU or GPU or anything else. So today, just want to take you through a few of the advantages that VPX provides for processing intensive applications. Talk a little bit about how VPX enables the MOSA, modular open system approach, with standards like SOSA and CMOS, and then talk a little bit about the future of VPX as well. So if from a high level, if you look at high performance computing and what's being done in the data center today. There's lots of great new technologies that are out there. They're, take up a lot of space. They take a lot of power. So the great thing about VPX is it allows you to harness that capability, but bring it into a nice rugged, swap optimized and secure ecosystem. And the whole idea that we try to focus on is how do you take those concepts and those capabilities and bring them into something that can be used, at the tactical edge in a defense or military aerospace platform, or, in other rugged environments as well, industrial, agriculture, any harsh environment where you need to do high performance computing. And this whole VPX ecosystem is really taking that technology all the way up at the chip vendors, the Intels, AMD, NVIDIA. They're providing chips that are available over a wide range of temperature now, and offering those chips over longer life cycles, and allowing module vendors to make use of that technology and put them in circuit cards where reliability, long life cycle is of the utmost importance, and creating a product that system integrators can put into a VPX system and put into a harsh environment. Nigel walked you through the VPX architecture and talked a lot about the different types of payload profile, the timing modules, the switches. But the VPX architecture, what it comes down to is really allowing a heterogeneous architecture. And when power is a concern, size, weight is a concern, you need to use the best tool for the job. So whether that be a CPU, a GPU, FPGAs, there's DPUs out there focused on, getting network data into a processor memory with little processor overhead. Specialized AI processors focused on the vector math and the neural network math that needs to be done to efficiently run those algorithms. Your the VPX architecture really allows you to pick the best processor for the job and do that job with the least amount of power, which in turn helps you really get your swap C down for your rugged system. The other nice thing about the VPX system is that it's really scalable. You can have a 1 slot backplane, you can have 10 plus slot backplane, and you can customize the cards that you want for the job that you have. So you might want a bunch of high-end CPUs, in a compute-intensive payload profile, or you may want to couple those processors with an FPGA and a GPU as well. And this VPX infrastructure really allows you to scale that system based for your needs, and that can easily change over time as well. And the bottom here, this architecture is really allowing you to use best-in-class silicon that has huge investment going into it every year, and bring those into the rugged system. And not only is this heterogeneous architecture happening at the system level, it's happening at the module level as you're starting to bring more chips onto one module, and even in the chip level themselves, where you're bringing different types of silicon down into one chip. Here's an example of a new wave 6061 FPGA module, and it actually has silicon from AMD, NVIDIA, and ARM all in that single module. So you're getting a versatile FPGA that has a huge FPGA fabric. You're getting hard ARM core processors in that module, and you're also getting the availability of AI processor that's geared towards doing neural network math as efficiently as possible. In addition, that module also has a Mellanox NVIDIA networking chip, which is optimized to bring large amounts of sensor data into the system and get those into the memory where the processors, the variety of processors can work on them. So, there's a real focus on trying to use the best processor that's going to use the least amount of power in your system. The next, important part of this is the VPX ecosystem really allows you to withstand harsh environments. There's a VITA 47 standard outlines a number of different environmental profiles that vendors can test their cards to, so that system integrators can be confident that their system is going to meet their environmental requirements. As Nigel mentioned, there's a number of different cooling methods that you can pick from to get the best cooling performance that you need for your specific requirements. You have air cooling, conduction cooling, the air flow through cooling that Nigel was talking about, and even liquid cooling. As you're trying to pull in the latest technology in high performance computing, it's not uncommon for some of these chips to take to put off hundreds of watts of power. So the cooling problem, especially in a dense VPX system, it can be very challenging, but there's nice options to get better and better from that perspective. So these set of common requirements and common test procedures really allow this whole ecosystem to work together and pull in that commercial technology into a rugged form factor where people can be confident that their system is going to meet the needs of their environment. The next important aspect of the VPX system is really the amount of sensor data that you can pull into the system for processing. Nigel talked a little bit about the RF and optical connectors you can see in the bottom left there in that 67.3 cutout. And you see, the standard backplane connector above, but there's, the ability to bring in both digital and analog sensor data, really high density optical data, and then the electrical interfaces to move that data back and forth from between CPUs, GPUs, FPGAs, in your system as well. So that really is key to enabling a specific VPX system to withstand the test of time. And as you're upgrading the processors in the system, having big pipes of sensor data to come in there really helps future-proof that box, and you can gain more capability as you move forward. We also see huge benefit in the latest network interfaces and offloads. You have 100 gig Ethernet supported in these systems, but oftentimes that's a huge task for a processor to handle, moving that data from one place to another. But protocols like Rocky V2 can help you offload that data and share that data among the different types of modules in the system without taking away from the processing power of a specific module. The other thing that this does allow is new types of sensor architectures where you can afford to keep your application processing further and further from the sensors. If you're digitizing your sensor data as close to the sensor as possible, you can now move that data over to the processing system over optics, and you really enable your system to have access to data from a variety of different sensors and come up with algorithms that can make use of all that data. It also helps keep hardware that can be used in multiple different modes as well. So as long as you have access to that sensor data, you can do lots of different things with it. So up to this point, we've been talking a lot about how VPX can really allow you to take advantage of the latest and greatest commercial technologies that exist. There also is a need to be able to handle old legacy technologies as well. When platforms do get upgraded, um, it's not always easy to upgrade sensors, and some sensors, are used throughout the life of a platform. And VPX does accommodate ways to utilize those old interfaces and get that data into your processing system. One way to do that is with mezzanine cards. In the example here, you see an XMC that would get mounted on IO intensive payload, a single board computer, and using that XMC, you can actually offload that specific protocol interface from the old sensor and move the data into the host system over PCI Express. And we've done a lot of that at New Wave, and there's other XMC vendors out there doing the same thing. But you can support old technologies like Fiber Channel and serial FPDP 17.1, 1394. They can be supported within the greater ecosystem of VPX, and when you want to upgrade your processor module, you can move that XMC to the new module, and you don't have to create a special card just to interface with the older technologies. All of these things that we're talking about in the VPX architecture are ultimately enabling the modular open system approach objectives, that SOSA is really taking and running with. It's really helping to keep the number of options that are available with OpenVPX and limit those to a set, so that suppliers can build modules that can support a wide range of applications, and they can invest their money into the latest and greatest commercial technologies, and that can be used by the broad community. And you have upgradability. You create competition among suppliers, and you can create hardware that supports multiple modes of operation. So that's really, SOSA's really helped move VPX in that direction. And you're getting into the situation where new businesses that maybe weren't able to participate in this can be part of these rapid innovation cycles as upgrades take place, not only from the hardware side, but from the software side too. You have, companies that might have a novel algorithm that can make use of that you can apply to a VPX system, and they wouldn't be able to provide all the hardware and all the infrastructure that goes along with this, but they can provide a great algorithm. So it's really opening up opportunities for new businesses and small businesses, and creating a nice ecosystem that's ultimately great for the system integrators as well. So as we move forward into the future, there's a number of challenges ahead. In order for VPX to continue enabling the latest in commercial technologies, updates and upgrades need to be met so that you can keep taking advantage of what's happening in the commercial world. There's new chip technologies coming out, new connectors. SerDes speeds keep getting faster and faster. Chips keep taking more and more power, so new thermal techniques need to be utilized. So it's important, as the next generation of VPX is being formed right now and requirements are being put together, that we can accommodate the latest and greatest on the commercial side and continue to bring that technology over to the mil-aero and defense markets. So in closing, I just want to highlight that VPX really does enable high performance computing in the rugged world by supporting heterogeneous architectures and high bandwidth sensor data. We're ultimately, continuing to push the edge of what integrators and module level suppliers can offer the customers today. And really excited to continue to see where this goes and can keep pushing the envelope of technology. So now I'll hand it back to John McHale so we can get some questions from the user group. Thanks.
Excellent presentation, Ryan, and same to Nigel. You guys did a great job. And there he is. He's back on screen. We haven't lost Nigel. That's really good news. So let's get to these questions, gentlemen. We've got a very interactive audience, and they want to learn more. So my first question is for Ryan. What are some of the available and future technologies being used in the commercial market today that could be valuable to the VPX ecosystem in the future?
So there's a number of interesting things happening out there. One area that I think is particularly interesting is the chiplets. We talked about the heterogeneous architectures and how that's moving into the chip level. You now have the ability to kind of custom make your own SoC using the pieces that are the best power and performance for your specific application. So you could, for example, create a chiplet with a large FPGA fabric, maybe processor, CPUs on there, hybrid memory, maybe some A to D, D to A converters. So there's just a lot of different things that can be explored, with that chiplet technology. And then a few others, integrated photonics or at the chip level are an interesting thing that's coming. So, right now, those are all external to the parts. They take a lot of power. We see that technology coming to the commercial world soon, and also integrated coax into the chips as well. So as we get push higher and higher speeds and move, in VPX right now, we're at 25 gig NRZ, but the commercial world's at 56 gig, 112 gig PAM4 type SerDes. There needs to be new options for routing those signals across the board and through the connectors. And so, connectors also are going to have to move forward and be able to handle those higher signals. And then I guess one other area too, the cache coherent interconnects. I mean, we have PCI Express on the backplane. We have Ethernet as well, but there's interfaces like CCIX and CXL that allow these heterogeneous architectures with multiple types of processors to access data all at the same time and work on that together. So I think that's an important piece that's upcoming as well.
Okay, thank you, sir. I got a question here for Nigel. Are these VPX-based building blocks only used in defense applications?
No, is the simple answer. It's fair to say that the majority probably are, because VPX fundamentally has great ruggedization environmental capabilities to work in a wide variety of environments. However, just to give you a couple of examples, in the last 12 months, we've seen a couple of applications in the transportation sector where the user's needs were to have something that would work in adverse environmental conditions at 24-hour operation. We also had a nice application in the electricity generation and distribution, where their fundamental requirement was to have some really reliable equipment to control the power distribution network and have the ability to maintain that over a very long life cycle. So not something you perhaps would have traditionally thought would work for VPX, but it fitted their needs perfectly.
Next question from the audience. Are there any plans to enable full immersion cooling in VPX? This is not assigned to anybody, so whoever wants this one.
I'll go first. That's a very interesting question. We've looked at that a couple of times. I would say not in the short term, in that we don't have anything that we'll be launching in the next 12 months. But we've had a couple of customers approach us with that potential in mind, because it's some technology that's now maybe not widely used, but it's certainly used effectively in the data center. We've been working with a couple of partners on investigating what might be possible within a VPX environment and what types of applications would best fit full immersion cooling. I'd be very interested to talk to the person who made that question, see if we can elicit some more useful customer feedback that we could actually incorporate from a technology perspective and maybe move that forward.
Ryan, anything you want to add to that one? Or?
Yeah, I would agree. I think it's a really promising technology and method of cooling. At the moment, in the near term, I agree. There hasn't been any discussions of particularly how to implement that, but we're seeing people talking about it more and customers more interested in it. So, I think there's a room for that in the future coming.
Okay. Next question from the audience. This one again is unassigned. What is the envisioned high limit operation for TSN, and how many endpoints can run at that upper limit concurrently? Who would like that one?
Well, TSN is a very good topic. It's quite a hot topic. We're seeing a lot of applications starting to require TSN, standing for time-sensitive networking. And that's because we're seeing a lot of the traditional real-time interfaces, the need to sort of migrate those away. So instead of having your CAN bus or your 1553 or your 429 interfaces, some of those are looking to migrate to time-sensitive networking. I personally don't know, I can't answer the exact question about how many endpoints can run at the upper limit, but I'll certainly take that away and get one of our technology guys to give you a good answer. But we're fundamentally seeing a lot of interest and real customer requirements coming through for time-sensitive networking. So it's definitely something to watch out for if you've not encountered it today.
Ryan, do you want to add anything?
Yeah, I would agree. We're definitely hearing a lot of talk about TSN and customers having TSN requirements as well. At this stage, primarily at 1 gig and 10 gig. I think there was a question on speeds. So that's what we're seeing today. We're ultimately trying to figure out where this will go as well, and will this be a part of the 40 gig, 100 gig networks at some time too. We'll need to find that out.
Okay. Next question from the audience, once again unassigned. This means I want to hear from both you guys. Help me understand or sell the swap advantages of 3U VPX versus 3U rugged COTS. With rugged COTS having Xeon Scalable versus Xeon D, do customers ever run into performance limitations? Who wants one?
Okay, so I'll take the first stab at that. Welcome Ryan's view as well. So absolutely, in a 3U physical format, we talked about the cooling infrastructure. So 3U is physically about the size of a postcard. So whereas a Xeon scalable processor, which goes up to, 250 type watts, it is, if you were going to fit one of those on a 3U VPX card, it would be incredibly difficult. And then to match that with the amount of memory that you need is even more challenging. But the real killer is that you can only cool so much capability within that physical form factor. And that's why there's been a move towards some of these more exotic cooling technologies like air flow through. So fundamentally, 3U VPX works really well where you want a mix of heterogeneous compute capability that Ryan eloquently talked about in his presentation. But there are limitations. You cannot fit a core into a pint pot, basically. So the Xeon D, currently the top end processor is about a 20 watt, but even at 20 watts, you're running at a very high power level where you probably have to scale the processor down to cool it. So it's a trade-off. There are some applications where VPX works really well. There are others where having a COTS, rugged server type architecture also works well. It's really, whatever fits best for your application.
Ryan?
Yeah, I would agree. And you kind of see the same thing on the FPGA side as well. I mean, the latest and greatest FPGAs, the Versal Premium series, for example, which familiar with the largest FPGA there, would be extremely hard to fit on a 3U card. And even the Versal Prime series FPGAs that we have on our cards, if you filled that thing up full and, you know, utilized all the CPUs and the AI cores on that, you would have a hard time keeping that cool in a 3U VPX module as well.
Okay. Next question from the audience, unassigned. So I'll throw it to both of you. How is redundancy for the 5.9's life-critical applications managed? Can you duplicate switches and timing boards? Would like to go first.
Yes, absolutely. The example backplanes that both Ryan and I showed didn't actually have duplicate domains, but that's exactly how you do it. You have a backplane that effectively is dual redundant with switches and payloads, and you have some way of switching between those two, depending on whether the right domain is active or not.
Ryan, anything you want to add? Or
no, I agree with that.
Okay. Next question I have is for Ryan. What are some ways you can put together a VPX system that will stay relevant and not become obsolete in a couple of years as commercial technologies continue to evolve? The obsolescence question. How do you do it?
So I think, you know, the SOSA architectures really help with that, because you have modularity and upgradability built in. You make your system, and as chip technologies evolve and new processors come out and new things come out, you can easily upgrade your system to use those. I think one of the keys here, though, is really making sure that you get as much sensor data into that system as you can, because the sensors are sometimes more difficult to upgrade, and they're integrated into certain places on the platform. So you know, if you could get that data digitized as early as possible and get as much sensor data into where you're going to be doing the application processing, then as new chips become available, and, you know, new technologies become available, algorithms become available, you still have all that data in your system to make use of.
Okay. Next question is for Nigel. Nigel, you mentioned high-speed fabrics like PCIe Gen 4 and 100 gig Ethernet. What's next?
Yeah, so there's always a next. So we're already starting to see PCIe Gen 5. I think maybe Ryan has PCIe Gen 5 on some of his personal cards today. So that's absolutely on the horizon. We're seeing people requesting even higher bandwidth Ethernet connectivity to 200 and 400 gigabit Ethernet. And Ryan mentioned things like Compute Express Link, CXL. Those types of capabilities internal to the card will make incredible gains for things like cache coherent applications. So there will, and on top of those, you've got, you know, a large proportion of VPX applications with direct optical connections or RF connections. We're bringing in far more data at far higher bandwidth speeds. So the standard's designed to be upgradable, and that's exactly what we expect to see.
Okay, looks like I got time for one more question, and this one is for Nigel. I don't need 10G or possibly 1G Ethernet data rates for my application. Isn't this overkill?
Yes, possibly. But what I would recommend is that you, if there is any possibility that in another 5 or 10 years time, your application speeds will be enhanced, then I'd strongly recommend at the very minimum putting in a backplane that is capable of much higher bandwidths. So all the sorts of cards that we talked about today are upgradable. There are technology insertions. So even if the payload cards and the switch card is only capable of, let's say, 1 gig Ethernet today, you can replace those very easily as time goes on, providing you've got the basic infrastructure in place to do so.
So it's kind of like in regards to this overkill. That's why 1553 is still around, because people think anything else is overkill.
Yeah,
never go away.
So think ahead and choose what's best for you today and in the future.
Exactly. All right, and that brings us right to our time limit for today. I'm sorry we can get to all of your questions. I'm going to make it back to you after the event with more information. I want to thank Ryan and Nigel for speaking today. Great job, guys. And New Wave DV and Concurrent Technology for sponsoring this webcast. This and all Open Systems Media webcasts are copyrighted. minute recorder used in any way without the express written consent of Open Systems Media. This event will be archived online today at the same URL you used to join today's live event, as well as the URL shown on your screen. It will be available for at least 1 year. I look forward to seeing you on future Open Systems Media webcasts. Have a good day.
Thanks.